The velocity of the wave, displacement over time, is something that we might be pretty familiar with by now, given that we've already worked quite a bit on displacement. So we can talk about this in the velocity in two different ways. We can say it's wavelength over period, because this will be the distance traveled, the wavelength, over the time that it took, the period. But hang on, don't we have an equation for period? We relate the period to the frequency. That means that we can measure the velocity of a wave with the wave equation. Velocity equals frequency times wavelength. So if we know the wavelength and we know the frequency, we can figure out exactly how fast the wave is going. The intensity of a wave is a measure of how much energy it carries. So for a sound wave, for example, very loud sounds will have a high intensity. Very soft sounds will have a low intensity. So it's measured by finding the energy flow through a plane perpendicular to the velocity. Now, what does this mean? It means that if we have a wave traveling left to right, then we're measuring how much energy it brings through a little square plane like that. So we're going to be measuring this in the amount of energy it brings over time per square meter. A sound wave has a velocity of 340 meters per second and a frequency of 256 Hz. Find its wavelength to three significant figures. I hope you remember your scientific notation rules. Alright, so how would we go about finding this? Well, we can use the wave equation. Can you remember how it goes? V equals F times lambda. So in this case, we're given V and we're given F, but we want to find lambda. So we need to rearrange our equation. We can see by dividing both sides by F that lambda will equal V over F. What we need to do now is substitute our V and our F. That gives us a value of 340 over 256, which evaluates to about 1.33 meters.